Welcome. Today I'm going to present to you how to make recommendation systems fast from the system's perspective. This is a joint work between ETH Zurich and Alibaba. Personalized recommendations are everywhere. It is used in e-commercial scenario, video websites, and social medias. So why do we care high-performance recommendation serving? Before answering this question, let's take a quick look at how a recommendation system looks at. So first, you have a candidate database containing your advertisement or video contents or etc. And the first step of this process is to select some candidates that the users are potentially interested in. For example, you can select 100 items out of our potentially millions of items and do a DNN-based scoring out of it. This DNN scoring will select the top 10 most relevant contents and recommend them to the user. It turns out to be this DNN-based scoring are actually quite heavy in data centers. According to some company, 80% of workloads running in some of their data centers are this DNN-based recommendation system. So it's pretty expensive. Besides that, the reason why we want to do candidate selection before the DNN scoring is due to the limited performance. Let's say if we can have the system 10x faster, then we can select more candidates. Previously, we just 100, but now we can use 1,000. And we still do the DNN scoring and recommend potentially more precise items to the users, which will potentially boost the revenue of the companies at all. Now let's take a look how the deep recommendation models look like. So you have some input features, you have dense part that will be fed into some fully connected layers. You also have some sparse features such as the user ID, and each sparse feature is corresponding to an embedding table. So this feature will be used as an entry to look up an embedding vector in the table, and all the embedding vectors are gathered together with the processed dense feature. The scatter feature will be fed into the top fully connected layer, and the click-through rate will be predicted, which stands for how likely the user will click on the item. However, this embedding table lookup pattern actually leads to a big problem in terms of systems performance. Because this is a machine learning conference, I'm going to do a quick recap about why this random DRAM access problem is a bottleneck. So in this example, we have two embedding tables. We first have the first lookup operation of table 1, which initial a short read. Why it's a short read? Well, because each embedding vectors are typically quite short, containing from 4 elements to 64 elements in most of the case. And this short read will activate the DRAM bank's row buffer. And when we issue the second lookup operation, it will jump to another address in the virtual memory and initial another short read. And it will flush away what is already in the row buffer and reactivate the row buffer. This leads to underutilized data bus, well, because those are just short random DRAM access instead of sequential DRAM access. It's pretty unfriendly to what the DRAM will favor. Another problem is that the machine learning frameworks today are not optimized for embedding table lookups. According to our observation on TensorFlow serving, which is already optimized for machine learning inference, there are 37 types of operators invoked in the embedding layer, such as gather, sparse across, etc. So we did some workload characteristic from 3 models from Alibaba. The model size ranges from 1 GB to over 100 GB. On the y-axis is the normalized latency. The blue part is the embedding layer's time consumption, and the green part is the fully connected layer time consumption. As you can see in the numbers here, over half of the time are actually spent on the embedding layer. So it's a quite significant bottleneck. Now we know that the embedding table lookup is one challenge because of the DRAM access and the machine learning framework overhead. Another challenge as other DNA inference is the heavy computation workload in DNA, which is basically some matrix multiplications. Also, we may need to serve some very large models for over 100 gigabytes, because if you want to encode, let's say, the user information, and if you have 1 billion user, then you will have a super large embedding table to store those embeddings. And this causes a problem because modern accelerators like GPUs and FPGAs, they do not have enough DRAM capacity to hold these very large models. And the final challenge is that there could be very tight latency constraint in real-time inference. For example, if you want to feed the user your recommendations in real time, then you may need to set a latency constraint of 10 milliseconds or so. And under this tight latency constraint, you still want to maximize your throughput, which means how many inference you can do within a second. And of course, there are a handful of existing solutions. One is GPU-based. GPU is known for its fast DNA computation. However, the embedding table lookup performance is not very well, although it has some high bandwidth memory. This is because the machine learning framework overhead. The many operator calls actually are not friendly to the GPU SIMD infrastructure. And also, GPU has high latency, because if you want to maximize the throughput of GPU, then you probably want to use batch size. So not only did you want to process a large amount of data at a time, you also need to wait a while for the user's query to arrive to gather those large batches. And finally, GPUs do not have sufficient memory for those like 100 gigabyte model. Another solution is FPGA-based. I picked one of those solutions here. It is equipped with high bandwidth memory. So as in the figure, there are some HBM channels, and HBM are basically some highly concurrent DRAM. In this case, there are 32 HBM banks that can be accessed concurrently and individually. So let's say if we have 100 embedding tables and there are 32 HBM banks, then we can split those tables in those individual banks. And for each bank, we only need to access them 3 or 4 times. So it's pretty efficient in terms of embedding table lookup. Besides DRAM, this FPGA also equips some DDR memory for some large tables, but of course with lower memory access concurrency. FPGA also have some fast on-chip memory that can be used to cache some small tables. So what FPGA do is that it receives some embedding table lookup entry and gather the embedding vectors from all this memory hierarchy, and then finally do the DNA computation to rate the click-through rate and return this to the CPU. So overall, this is very fast in terms of embedding table lookup, because there's no ML framework overhead and you have sufficient memory concurrency. However, FPGAs are known as very slow in terms of DNA computation. I mean, at least one order of magnitude slower than GPU. And also, the HBM is even more scarce resource on FPGA. In this case, only 8 gigabytes, but definitely not sufficient to serve any very large recommendation models. So in the insight of this paper is that, can we take advantage of the strength of multiple types of hardware while avoiding all of their weaknesses? So for GPU, we only wanted to do the DNA computation without any embedding table lookup. For FPGA, we can use it as a customized memory controller for the embedding layer, but not do any DNA computation. We can also take advantage of CPU's DRAM because they are cheap and sufficient for holding some of the largest embedding tables. So the naive idea is that we can install some GPUs and FPGAs on the same server. But is this a good idea? Well, there are many types of recommendation models, and some of them are more memory access intensive, for which you may need more FPGA to do the embedding table lookup. Well, for some other models, it may only have a few embedding tables, and it's intensive on computation, for which GPUs are more important. So if we want to set up the ratio on the server, how many FPGAs and how many GPUs you want to install on, then you are restricting yourself, because when serving different models, other type of the hardware will be underutilized. And another problem is that the current data center do not have any servers that install GPUs and FPGAs on the same server. So you can rarely find any of them. In this paper, we propose Fleetrec, a hybrid recommendation system consisting CPUs, GPUs, and FPGAs. And those nodes are interconnected by network instead of installing on the same server. On the left-hand side, on the top, we have a GPU host server. Let's say we have a host server containing 8 V100 GPU, which is commonly which you can commonly find in any cloud providers. And on the bottom, you have similarly a host server with several FPGAs. And our solution is that on the FPGA, we add a network stack, a TCP network stack that can receive the recommendation request and parse the request to look up the embedding tables on FPGA and finish the embedding gathering, and then return the gathered vector to the GPU's host server. The GPU's host server then send this gathered vector to GPU to do the computation part only. In this case, we can still combine one GPU and one FPGA, no problem. For the case of very large embedding tables, we can use one remote CPU node that has sufficient DRAM and 2 FPGAs for medium and small sized embedding tables, and couple them with one GPU for computation. So very flexible combination. And even more cool, we can also do some multi-tenant stuff. I mean, by splitting the FPGA by half, each half of them serve individual recommendation model. So in the left-hand side, the model B, we can couple half of the FPGA with 2 GPUs. In the case that the computation is more intensive compared with the embedding table lookup. You probably also have some leftover FPGAs for GPUs, which you can perform any other task other than recommendation. In this case, we can do some database operator acceleration, so ideally, no waste of those hardwares at all. Fleetrec achieves significant speed up compared to the CPU and FPGA baseline. We still measure the 3 models of different batch sizes, ranges from 1 gigabyte to over 100 gigabyte. And for the small and medium model, we have CPU baseline and FPGA baseline. For the Fleetrec side, we use 1 FPGA and 1 GPU as the comparison. As you can see here, compared with FPGA, we get around 10x speed up, and compared with CPU, we even get an astonishing 50x speed up. So it's quite significant. For the over 100 gigabyte model, the FPGA baseline may not apply anymore because of the limited DRAM resource. And in order to evaluate this larger model, we also upgrade our hardware. For CPU, we have doubled core and DRAM channels. For Fleetrec, we add 1 CPU nodes for the large embedding tables, and we also use 2 FPGAs for medium small embedding tables. In this case, we still achieve more than 1 magnitude of speed up compared with the CPU baseline. We also achieve significant latency reduction. For the small and medium model, we achieved 90% latency reduction to less than 5 milliseconds. And for the large one, we still achieve 20% latency reduction, which is not as significant as before because right now we use 3 storage nodes, 2 FPGA and 1 CPU holding the embedding table, and the GPU server need to do some coordination. I mean, synchronization between those 3 nodes. So some additional overhead there, but still, even if we use 3 storage nodes, it's still faster than the 1 single node CPU baseline. For real-time recommendation, Fleetrec is even more advantageous. Let's say we set the latency constraint to 5 to 20 milliseconds. In a 10 millisecond scenario, we achieve 40x to almost 400x speed up compared with CPU. And if we have even more strict latency constraint like 5 milliseconds, then CPU cannot do it at all, no matter batch size we use. But Fleetrec can achieve it. To conclude this talk, serving recommendation models efficiently is very important, but also very challenging. The first challenge is the embedding table lookup operation, which involves many random DRAM access. It is also worth to mention that the modern machine learning framework invokes many operator, which is not friendly to embedding table lookup as well. Also, the second challenge is the DNN computation, just as other models. And the third challenge is serving models over 100 gigabyte. And the final one is to optimizing the throughput under strict latency constraint. In this paper, we propose Fleetrec that takes advantage of both CPUs and GPUs and FPGAs, and the system can perform very good, both in terms of computation and embedding table lookup. It also allows flexible combination of the hardware, so there's no underutilized hardware in the cluster. It also not require any special cluster configuration, installing GPUs and FPGAs on the same server. So deploying this system in data center can be very easy. With this, I would like to end this talk, and I'm looking forward to all of your questions.